Welcome everyone to our bi-weekly expedition seminar series. It's a great pleasure to have Michela Meister, who's going to join us today and speak about her work with Professor Jon Kleinberg, who is also online. Michela did her BS and MS at Stanford University in the computer science department, and after working at Google Research, has joined Jon as a PhD candidate in computer science. She's done some very exciting work, but the specific work that she's going to talk about today is about containing the spread of a contagion on a tree. And we look forward to your talk, Michela. Thank you.
Thanks so much for having me. So today I'm going to talk about some joint work with my advisor, Jon Kleinberg, on containing the spread of a contagion on a tree. And just to sort of situate this talk, we can think about models of infection as ranging from more theoretical to more applied. And we can also categorize them by whether they include some sort of degree of intervention. And our focus today is going to be in the upper left-hand quadrant. So we're going to be looking at algorithmic and mathematical problems in contact tracing. So for today's talk, we're going to be thinking about contact tracing as the process of recursively identifying infected individuals and their contacts. And we're going to be thinking about this in manual tracing setting. And as I said, it seems that very few mathematical models of contact tracing exist, despite the fact that there are many mathematical models of infections and epidemics. And we're going to develop a model that's a race between two processes. So there's an infection process where people meet and make new contacts, and where infected individuals probabilistically infect each new person they meet. And then there's going to be a tracing process where a tracer quarantines or stabilizes individuals, which then stops them from meeting new contacts and further spreading the infection. And the tracing goal is to stabilize all the infected individuals so as to halt the spread of the infection. So to start out, I'll describe the infection process. And as I describe the model, feel free to stop me and ask any questions along the way. So to start out, each individual is going to be represented by a node. And at time t = 0, a single root A exists. And at each step t, each node meets a new contact with contact probability q. So in the case where q = 1, this means that each person meets one new person each day. So to see an example, in the case where q = 1, we have at time 0, a single root A. At time 1, A meets B. At time 2, A meets C and B meets D, and so on. And we say that a node that arrives at time t = tau has arrival time tau. So here, A has arrival time 0, B has arrival time 1, C and D have arrival time 2, and so on. Now to describe how the infection propagates, at time 0, the root A is infected with infection probability P. And then at each step T, an infected node infects each new contact they meet with infection probability P. So are there any questions about how the infection process works so far?
Just a quick question. So once a node is infected, does it remain infected throughout?
Yes.
Okay.
Yes. Great question. Next, I'll describe the tracing process. A single tracer arrives at time k and queries the root A. And querying a node reveals its infection status. If the queried node is infected, then its children are revealed along with the age of each child, and the node is stabilized, which means it stops generating new children on future steps. And at each step from then on, the tracer queries one node. And the constraint is that the tracer may only query a node if it is the child of an infected node that was queried in the past. And we call this candidate set of nodes that might be queried the frontier. Okay, so next I'm going to describe how this infection process and tracing process combine to form the full model. Are there any questions about the tracing so far? Okay. So to describe the full model, we say that an active node is any node which has not been stabilized. So the full model will work as follows. For the first k steps, an infection round runs, where each active node U generates a child V with contact probability Q. And if U is infected, it infects V with infection probability P. Then from time step K onward, first a round of tracing occurs where the tracer queries a node W from the frontier. And if W is infected, it's stabilized. And then another round of infection occurs. To see how this works, we'll do an example. So here we're going to be working with the lateness parameter K equals 3 and contact probability Q equals 1. Because K equals 3, for the first 3 time steps, the infection is going to run uninhibited. Then at time 3, the tracer queries the root A, and in this case, A is infected. Then at the following step, the infection process runs again. So all of the active nodes, which right now are all the nodes except for A, generate one new child. And they generate exactly one new child because we're assuming that the contact probability Q equals 1. Then at time 4, the tracer needs to make a choice. So the frontier on the previous step included nodes B and C. Here, the tracer's chosen to query C, and C is infected. And so now, after time step 4, the frontier includes nodes B and F. Okay, and then another round of the infection process runs.
Yeah, Michela, can you go through the steps 3 to 4 again, please?
Yeah. So in the first step, the tracer queries the root A because that's the only node in the frontier. That's the only node available. A is infected. So this means that its children are now going to join the frontier because the tracer is allowed to query any node, which is the child of an infected node, which they've already queried in the past. Okay, so that's the state after the tracing round at time 3.
So at this point, A, B, and C are known to tracers.
Yes. And the tracer also knows the ages of the nodes. So, for example, the tracer knows that B is older than C and can infer that B might then have more children than C.
Okay.
So yeah, so the tracing round happens first, and then the infection round happens. And the infection round is every node which hasn't been traced generates a new child with probability Q. So here, because Q equals 1, B, C, and D each generate a new child.
But A doesn't because it was picked up by the tracer as
Exactly.
quarantine.
Yeah, exactly. So A can no longer generate children. Yeah. Okay, and so now we're about to head into another tracing round. The yellow band shows the nodes in the frontier. So now the tracer could query B or it could query C. And just in this example, it queries C. So because C is infected, C's child F is now also available in the frontier. If C weren't infected, F would not join the frontier.
But so the nodes in the frontier's disease state is not known.
Correct. Yeah. Nodes in the frontier are all the children of infected nodes queried in the past that haven't been queried yet.
Yeah, so so the disease state is not known, but they could potentially be infected. Yeah. Okay.
Exactly. Yeah. And then the final step is another infection step.
And if the budget was 1 for query, right? Every step you were only allowed to query 1 node. So trace 1 node, pick 1 node from the frontier.
Yeah, every step you're allowed to query exactly 1 node. So the contact probability Q, we can sort of toggle that to speed up or slow down the growth of the tree. So if you wanted to think about allowing the tracer to work faster, you can think about decreasing Q.
Yeah, got it. Thanks.
So we say that the infection is contained if there's a time t at which all infected nodes have been stabilized. And we say that a policy is any function that maps the frontier to a choice of which node to query next. And our main question is, how does the tracer's policy for querying nodes affect the probability that the infection is contained. And so just to give an outline of the rest of the talk, I'm going to start out by doing a brief overview of some related work. Then I'll discuss some basic theoretical properties of the model. We'll look at a couple harder questions via computational simulations. And if there's time, I'll discuss some of our work at looking at optimal policies via a simpler variant of the problem, which we study with a technique called branching bandits. Probably the work that's closest to ours is a couple papers by Armbruster and Brando, which experiment with different ways of prioritizing contacts for tracing. But sort of the main focus of their work is to figure out how to optimally allocate resources between two different interventions, a tracing and a screening intervention. They're a little less focused on figuring out what an optimal policy might look like. Our work is also related to different tree search problems from computer science, but it still really seems like there's sort of a gap between mathematical models of contact tracing, in which there seem to be very few, whereas on the other hand, we have tons of work in public health on prioritizing contacts for tracing, which is the figure on the right. And so to start out, we'll look at some basic theoretical bounds. So here I have a chart with P, the infection probability on the y-axis, and Q, the contact probability on the x-axis. And we have bounds that at a high level say that if you're in this blue region where at least one of P or Q is very low, then any policy is going to contain the infection with high probability, which you might intuitively expect. Likewise, if you're in this red region where P and Q are both very high, then if you look at any fixed policy, P with high probability, P will not contain the infection. And so one of our main questions is below, is there an instance of these parameters, P, Q, and K, where the choice of policy affects the probability of containment? And this is what we're going to look at next. Our first theorem, informally, is that there is an instance, PQK, in which two policies have different probabilities of containment. And the two policies that we're going to look at are youngest first, which always queries the youngest node in the frontier, and oldest first, which always queries the oldest node in the frontier. And what we're going to do is we're going to show that there are settings of P, Q, and K where these two differ in their probability of containment. Okay, so first, let's just understand how these two policies work. This is going back to the beginning of the example we saw a few slides ago. And remember that at the end of time 3, the tracer had to make this decision between querying node B or querying node C. And here we know that B arrived at time 1 and C arrived at time 2. So B is older than C. So this means that the youngest first policy will query C. Okay, so here we see the youngest first policy is queried C. Now C's child F has joined the frontier. And then another round of infection proceeds. Okay, on the other hand, the oldest first policy will query B because B is older than C. Okay, so if B is infected, that means that its two children would then join the frontier, and then another round of infection would occur. Okay, and so the formal statement of our theorem is that for P very close to 1, and Q equal to 1, and K equal to 3, if we let P young be the probability of containment for youngest first, and P old be the probability of containment for oldest first, then we can show that P young is strictly larger than P old. And one of the key lemmas that we're going to use to give this proof sketch is this subtree lemma, which basically says that if a policy P queries a node of V, which already has age at least 3, given these parameters of P, Q, and K, then with high probability, P fails to contain the infection in the subtree rooted at V. So this will be the main fact we're going to use along the way. So here I've just pasted the two trees that we saw before, the result at time t equals 4 for the youngest first policy and the oldest first policy. We'll now look at the decisions that the two policies need to make. First, we can look at the left-hand side. We see youngest first queries C at time t equals 4 when C has age 2. And it's going to query B at time t sometime in the future, so at least 5, where B has age at least 3. And so this means that the subtree lemma is going to apply to B. Okay, now let's look at oldest first. So oldest first queried B at time 4 when B already had age 3. So again, the subtree lemma is going to apply to B. And it's going to query C at some time in the future at time sometime greater than 5 when C is going to have age at least 3. So again, the subtree lemma applies to C. The main question that we have here then is, what's the probability that youngest first contains the infection in the subtree rooted at C? And what we're going to show is that actually youngest first contains the infection in the subtree rooted at C with probability 1. And this is what I'll show next, but basically this gap is going to allow us to prove that youngest first has a strictly higher probability of containment. Okay, so let's see how youngest first is going to contain the infection in the subtree rooted at C. Okay, so here we're starting at the end of time 4. And right now I'm just going to ignore the subtree of B. So the next step is going to be a tracing step, time 5. And because youngest first always is querying the youngest node in the frontier, youngest first has to query F at time 5 because F is younger than B. Now, if F is infected, then its child L is going to join the frontier. And then another round of infection is going to occur. Now, on the next step, L is younger than B, and so youngest first queries L, and this process continues. So basically, because the descendants of C are always younger than B, youngest first is going to query the descendants of C, which ends up leading to this long chain. And because P is strictly less than 1, with probability 1, youngest first contains the infection in the subtree rooted at C. Are there any questions about this sort of proof sketch?
I think it's a very nice idea, and intuitively I can see it. So for C, given its youngest, is that the case that it will only have one child every time, or the tree can grow depending on when the query was done? Your example, of course, shows a linear structure, but is it the case that otherwise I'm not able to see it? Maybe you can help me.
Yeah, that's a great question. So this is mainly coming from the fact that each active node is going to grow one child at each step. And basically, because it's sort of like the tracer is just one step behind the infection. And so the node never gets a chance to have 2 children.
Okay.
If you delayed it by 1 step, then it would, there would be a node with 2 children here.
Okay.
Yeah.
I have a question as well.
Yeah.
So containment in this context is relative to the node that's identified. So like in this example, you said C, but I guess the containment probability doesn't say anything about like the global magnitude of the epidemic, right? Is that like what you're saying? Okay.
Yeah. So this little proof sketch here was just to show that we're containing. Yeah. Here we're just focused on containing the infection in C's subtree, with the goal of then being able to show that youngest first overall has a higher probability of containment than oldest first.
Okay, thanks.
Yeah, totally. Yeah. I mean, B's subtree could have, plenty of infected nodes in it. Yeah.
No, I had a question. B must have children as well, right?
Yes.
So why is it that they are not being picked up?
Let me go back a couple slides. So the big picture for the proof sketch is that we have this subtree lemma, which shows that if you're late to query a node, like if it already has H3, then with high probability, the policy will never contain the infection in that subtree. So here, because B had been queried when it already had H3, we could apply that lemma. And the only node that we couldn't apply that lemma to was C in the case of youngest first. So that's why in the proof sketch, I'm only looking at C.
So it's a policy thing, right? So when you say youngest first,
Yeah.
but though when you say youngest first, you should be considering any candidate which is the youngest. And here you have multiple nodes coming from this children as children of B and children of C as potential candidates, right?
So the potential candidates are the frontier nodes in the yellow circles.
Oh, I see. Okay.
Yeah, so you're totally right that B has many children who are younger. And the constraint is that the tracer can only query the children of infected nodes that they've already queried. Yeah,
So
so
from the
that's,
candidate pool of frontier nodes.
yes.
Okay.
Yeah.
Thank you.
Yeah, choosing the youngest node from the candidate set.
Okay.
Yeah.
Intuitively, it seems like once you reach time 3, tree has already exploded, and so there is not much value. The speed at which you can trace is completely overwhelmed by the speed of the growth of the tree, and so you essentially can't do much with that tree. Is that a reasonably good understanding?
Yes. Yeah. Okay. So we're going to now switch gears a little bit and look at sort of an experimental setup for this problem. So the sort of high level question that we're wondering is it the case that this youngest first policy is always going to outperform oldest first? And to answer that question, we ran a set of computational experiments. So the way this setup works is for an instance of P and Q with the lateness parameter K fixed at 3, we simulate the infection and tracing processes following the same model that I've described before. But now to deal with the idea of containment, we need some heuristic to decide when the infection has run to infinity. So we basically run these simulations until either the infection is contained or until the number of active infected nodes exceeds a constant C. So then for all infection probabilities P from 0 to 1, ranging in increments of 0.01, and all contact probabilities Q in increments of 0.01, for each instance of these two parameters, we're going to run on the order of 7 million trials for each policy. And we say that our observed probability of containment is the fraction of trials where the infection is contained. Next, I'll show some heat maps that show the results of these experiments for youngest first and oldest first. And as you might expect, these will look pretty similar to the theoretical bounds that I showed at the beginning, where when P and Q are small, there's a high probability of containment, and when P and Q are both large, there's a lower probability of containment. Here on the left, we have youngest first, and on the right, we have oldest first. And these are showing the probabilities of containment. So yellow is high probability of containment, darker colors are lower probability of containment. And as we see, this looks pretty similar to what our theoretical bounds would expect. So in order to compare these two policies, though, we wanted to look at the difference between the probabilities of containment. And so we took the difference between the observed probabilities of containment in these experiments. And then in instances where this difference was at least this constant, we ran a second set of trials. And we ended up running a very large number of trials in the second round. Our main goal was to see whether we could find more gaps between these two policies. Okay, so these are the results of the second round of trials. I'm just going to describe what's going on in this plot. So the yellow region is where youngest first dominates with confidence at least a half. And the green region is where oldest first dominates with confidence at least a half. And purple and blue are points where we didn't have sufficient confidence. Okay, now we have a couple interesting points on this plot. Okay, so in the top right-hand corner, this is the regime that we just saw for the proof of youngest first dominating oldest first. And then in the bottom right corner, we ran a series of trials to show that with very high probability, there's also a pair of parameters where oldest first dominates. So we don't have a proof yet of the setting where oldest first dominates. I think that would be a really interesting question to look at. But we do at least have, these 2 points where we know youngest first dominates at this point, oldest first dominates with high probability at this point, and then, these two larger regions where we see a difference.
So Michela, just to clarify, the oldest first part is an empirical result.
Yes.
That you pointed out,
Yes.
but the top one, of course, you had a proof that you
Yes.
should. That's what you're saying is open to trying to do the proof. Okay. Thanks.
Yeah. Having like a complementary proof for the oldest first section. I think another really interesting question is to try to understand this green band arc and what's causing that structure there. Yeah, so I think there are a lot of interesting questions out of the experiments. Okay, so thinking about what we've looked at so far, so we've had this model, this current model, which we'll call our dynamic model, where there's concurrent infection and tracing processes, and where we have this binary objective of containing the infection. And these experimental results show that there are regions of dominance for both the youngest first policy and the oldest first policy. And next question is, can we identify provably optimal policies? And to try to start thinking about this model, we started with a simplified variant of the problem, which we'll call the static model. And in the static model, instead of having concurrent infection and tracing processes, we've split these into 2 phases. So in the first phase, the infection spreads throughout the population, and then the process locks down. So the infection stops spreading, no new infections occur. And in the second phase, contact tracing proceeds. And the objective is to find infected individuals quickly so as to maximize a total benefit. And in this simplified variant of the problem, we're able to construct an optimal policy via a reduction to the branching bandits problem, which has generally been used for scheduling type problems in operations research. But at least to our knowledge, previously hadn't been used in a contact tracing model. So with the time remaining, I'm going to describe the static model, and I'll sort of describe as much as I can with the time remaining, but also happy to continue having questions along the way. Okay, so at a high level in the static model, we have the first phase, which is the infection process, where people meet, make new contacts over multiple steps, and infected individuals probabilistically infect each new contact they meet. Then the population goes into lockdown. And then in phase 2, no new infections occur, contact tracing proceeds, and our objective is to find infected individuals quickly so as to maximize this total benefit, where we're going to say that the benefit of querying a node that's been infected for tau steps is e to the negative beta tau. Let's think about analyzing the static model. So here we have a root which has age h. And right now we're going to consider a model similar to the one we looked at before, where q equals 1 and each node meets one new contact each day, but all of our results can be extended to cases where q is less than 1. Okay, this infected node of root h has children ranging in age from 0 to h minus 1. And the tracer needs to select an age from these children to query next. And by our definition of benefit, the benefit of querying an infected node decays with time. So this means that this node on the left, the child which is the oldest, has a low immediate benefit, but this child also has many descendants. So this might, expand our frontier. Now, the child on the right, the child of age 0, has high immediate benefit because it's young, but no descendants. So if we query that node, we may not be able to further expand our frontier. And so the main question is, how should we trade off the immediate benefit of querying a node versus access to its descendants? And so the general roadmap is that we show that our model of contact tracing reduces to the branching bandit problem, which was developed by Weiss in 1988. And Weiss's paper provides a construction for optimal policies in the branching bandit model. But this construction on its own doesn't describe a policy explicitly. So we analyze this construction to find explicit optimal policies for our models. And our informal selected result is that the optimal policy queries the youngest node first. I'm now going to just quickly describe the branching bandits model and show how this relates to our model of contact tracing. Okay, so in the branching bandits model, when you pull an arm, you receive a reward, and then that arm is replaced by a set of new arms. So more formally, there are arms of classes 1 through L, and the system is defined by a state N1 through NL, where Ni is the number of arms of class I. And pulling an arm of class I returns a stochastic reward Ri, and the arm is replaced by a multi-set of new arms. And a reward that's received at time t is discounted by e to the negative eta t. And the goal is to find a policy for pulling arms which maximizes the total expected discounted reward. So the main question which Weiss asked is, given a state, what is the optimal arm to pull? And he showed that there's a function which assigns each class an index such that the optimal choice is to select the available arm with the highest index. And so our informal theorem is that this static model of contact tracing reduces to the branching bandit problem, where at a high level, we map nodes to arms, we map ages to classes, so ages of nodes to classes of arms, benefit to reward, and we show that querying a node can be seen as equivalent to pulling an arm. And one of our main theorems for the static model is that for any beta strictly larger than 0 and any transmission probability P, the optimal policy queries nodes in order of age. And so by this, I mean the optimal policy queries the youngest node in the frontier, which we can think of as a priority ordering on the ages 0 through t. This equivalently says that the optimal priority ordering is to always query a node of age 0 if it's available, then always query a node of age 1 if it's available, and so on. Now I'm going to give a quick proof sketch of this proof, showing that this priority ordering is optimal. And this is going to be a proof by induction. To start out, we'll show the base case. So this means that if a node of age 0 is available, it should always be queried first. Recall that we need to select an age from the frontier, and benefit is time discounted. If it's infected, a node of age 0 will return the highest benefit of all nodes in the system. And because we have a constant probability P of infection, all frontier nodes are infected with the same probability. So this means that a node of age 0 has the highest immediate expected benefit in the system. And because our benefit is time discounted, this means we should always query that node first. Now that we have the base case, we're now going to first assume that this prefix of the priority ordering, sigma 0 through sigma k minus 1, if we set this prefix to be 0 through k minus 1, that is the optimal prefix. And so to start out, let's consider ages k and j, where j is larger than k. Now, this implies that k and j are lower priority than any of the ages in the prefix. So let's look at two nodes here. And let's suppose that these are both in the frontier. And we have to choose which one to query next. So if we query k, and k is infected, then its children join the frontier. And note that all of these children are in the prefix. And so by assumption, we need to query all of these children in the green band before we even consider querying j. And in fact, because of the recursive structure of the trees, we know that any descendants of those children are also in the prefix. And so this means we need to recursively query this green forest according to the prefix before we even consider querying j. Now we could consider the opposite case where we first query j, find that it's infected. Okay, it also has children in the prefix. And as argued before, we would actually need to recursively query this entire green forest according to the prefix ordering before we query any other nodes. And so the idea is that we, in either case, would have to first either query k and then the green forest, or first query j and then the green forest before making any other decisions. And we can write out the benefit of these two choices as the benefit of querying the node k plus the benefit of querying the forest, or the benefit of querying node j plus the benefit of querying the green forest. And now, because k is smaller than j, this means that the benefit of querying k is strictly larger than the benefit of querying j, which then implies that sigma k should be k. Now, I know that this has sort of been a quick proof sketch, and to sort of formalize this entire process, there's a lot of other work we need to do. So a lot of this work in formalizing this process, we do via the reduction to Weiss's branching bandit problem. And so we use the properties of the branching bandit problem in order to sort of finish off this proof. Most importantly, we would need to show that this optimal priority ordering would induce an optimal policy. And we get all of that through the reduction to the branching bandits problem. We've looked at a couple of different models and problems. And we've discussed this algorithmic framework of contact tracing. We've showed this clean connection between contact tracing and the branching bandits problem. We've looked at this dynamic model, both in terms of showing this strict inequality between the two policies, youngest first and oldest first, which we also showed via experimental results. And I think there are a lot of interesting questions going forward, specifically in trying to understand whether we can extend any of the optimal policy results in the static model to a dynamic concurrent model. And in addition, in trying to understand the simulation and experimental results in the dynamic model further, in particular, getting a complementary proof for the oldest first region. And that's all I have for today. So thank you very much. And I'm happy to take any other questions.
First of all, I want to thank you for a very nice talk. We were aware of your static result. Perhaps we're not aware of the other one as much. With Arvind and Anil and others, we actually have studied another version of this. I think your version takes care of this process of contact tracing. We looked at it at one time step part, but then we looked at it over a graph rather than a tree. So I'll share that paper with you.
Yeah, thank you.
Takes a slightly different view. I think both views probably have to be pull together to get the final result. So,
Yeah.
and the other thing that I wanted to mention, and I will send you the paper, that's a largely experimental paper. But the good thing is that was done with our colleagues at the Department of Health. And we actually studied and thought through the youngest and oldest policies. There were some caveats in it, of course. It turned out there's other advantage you have for the youngest first is after a while, the node becomes stale in any case, and the person recovers
Yeah.
from this part. So in that sense, at least as a heuristic, younger ones are preferred. The one problem, there were other sort of modeling issues. So that particular work has built out a simulation and a model where we do the studies. And in fact, they used some of our results. We don't know the details. The times were such that we didn't want to discuss exactly what happened, but the work we did influence how they ended up evaluating their policies. I'll share those papers with you. We'd
Yeah,
love
thank
to
you.
talk to you more about it. This is really fascinating work, but I'll stop here and let others ask.
Thank you.
So thank you for this great talk. So one question I had was looking at the definition of your process. It seems to be defined on an underlying graph, which is a complete graph, right? Because any node can be chosen as a neighbor for an infected node.
So we're thinking of it as, do you mean any node could be
If the tree grows, it grows on a complete graph, right? Because it doesn't make a, so maybe I misunderstood. So is there an underlying graph to begin with, or is it just a pool of nodes?
It's just a pool of nodes.
Right.
Yeah.
So it can be viewed as a complete graph because any node can infect.
Has the potential of, yes, any node has the potential of being a child of another node.
An infected node, yes. So question is, how would your policies change, or how could you use your methods for an arbitrary graph if this process was run on an arbitrary graph where you could only pick a child from the neighborhood, not
just to make sure I understand the question, like some nodes have access to a certain pool of people that could become their children, and other nodes have access to a different pool of people who'd become their children.
Yes.
Yeah, that's an interesting question. Yeah, I guess here in this model, we're thinking that each node will, grow a child with this contact probability Q. So I'm wondering, in the problem you're thinking about, would that be like you could grow children from your pool until your pool runs out and is empty?
Yes.
Yeah. So I feel like then maybe you want some way of prioritizing nodes that includes their pool size or neighborhood size, however you're sort of thinking about the people they have access to. Yeah, that's really interesting. I haven't thought about that.
Okay.
Yeah.
Thank you.
Thank you. Yeah.
This is Xijun from the Mathematical Biocomplexity Group. This is great talk, very, very inspiring, very fascinating. So I have a question, is like, see if I understand things correctly. Because essentially, the flavor of your talk have a feeling of breadth first search versus depth first search. And then if your policy would depend only on the age distribution of your frontier, that's the only potential factor that affects your policy, right? Because that's all you know.
Mm-hmm.
And then you have showcased in this example that at some points, either by proving theorems or looking at experimental results, and you have showcased that there are some cases that always choose the oldest, always choose the youngest. Mm-hmm. My question is more about like philosophical, is in principle, ideally, you can make decision based on the complete age distribution of the nodes in your frontier. Is there any situation that's choosing somewhere in the middle? Is it possible, or it is actually not possible? And then why do you believe that is possible or not? It's just like, I'm just asking about feelings, not because it's really interesting. Yes.
Yeah, that's a great question. And thank you for asking that. So I have like two answers, one for each of the models that we looked at. So in the dynamic model, after running all of the experiments I showed you, we were sort of wondering, okay, if we're prioritizing nodes by age, why only look at these two extremes? What if there was some other way of
Yes.
prioritizing by age. And I ended up running a set of other experiments. I basically modeled it as like a reinforcement learning game, where we're trying to search over different policies. Again, the policies, like you said, were just age-based
Yes.
policies.
Yes.
And so I did a sort of a heuristic search over policies, and then we found that none of those policies ended up outperforming the two youngest first.
The extreme, yes.
The extremes. And I mean, that doesn't rule out the existing policies, because this was just a sort of heuristic search, but it did give us confidence that these are the at least two policies for us to examine in this paper. So then in the static model, so here in this talk, I described our results for the setting where the probability of infection is constant. And we look at a couple other models in our paper. So we look at another model where the probability of infection decays with time. And in that model, we end up showing through the same type of proof structure that the optimal policy is this sort of interleaved policy where you look at the frontier, and either the optimal thing is to query the oldest node in the frontier or to query the youngest node in the frontier. And depending on the parameters, policy might be first these ages, old ages, then these young ages. So there are other situations where there are other really interesting policies to consider, and which are, at least in the static model, optimal. And yeah, it's definitely a really interesting question for the dynamic model as well.
Cool. Yeah, thank you very much.
Thank you for that question. Yeah.
Thank you very much for a nice talk. So the reward function that you take is already inversely proportional to the age distribution, right? I mean, the age at that time. So the youngest node will give you the maximum reward.
Yeah.
And that gives you an intuition that the youngest would be the best policy in some cases, right? So is it also possible to update your reward function based on how much you are leaving by not considering other nodes of higher ages? Or so what part you are leaving if you consider a node with age tau, how much you are leaving outside? So the chances that the infection is contained in some other node than the node with age tau, is it possible to somehow update your reward function based on that?
Okay, so a couple of things. Yeah, so that's a great question, in that in the static model, we're sort of wedded to that reward function in order to reduce our problem to the branching bandits problem. But I think your question is important for considering how we might be able to like move results from the static model to a dynamic model. Because like in the static model, we aren't really worried about containing the infection. We're just trying to maximize this reward function. And I think, so I don't really have a good answer to your question, except that this seems to just to be like key to applying any kind of intuition from the static model to the dynamic model. And that in the dynamic model, if you're querying a node over here, you're allowing more infections to spread in another region, and it's not totally clear how to balance those two out. So yeah, I don't feel like I have a good answer, except that I think it's really interesting.
Thanks. And is there any intuition behind this green curve that we see in this middle graph? Like, how do you get that?
Yeah, that's another area I don't really have an intuition for, specifically like why it's not symmetric. I think being able to characterize that curve would be really interesting. I'm not really sure about that. I have a lot more questions than answers there.
We are out of time for today, so we'll close it here. But I just want to say thank you again to our speaker, Michela, for a wonderful talk. And thanks, everyone, for joining us.
Thank you all. I really appreciate it.
Thank you very much, Michela and John. A really pleasure to hear. And I'll be in touch with you. And
thank you so much.
Yeah, the group is doing. Thanks.
Thanks.
Bye, everyone.
Thanks very much.